Hi everyone, welcome to our OpenPOWER Developer Challenge Hangout on using NVIDIA GPUs on OpenPOWER. Today on our Hangout, we're going to introduce you to the team on the call and then get a high-level introduction to NVIDIA GPUs. And then we're going to go through a demo that will show you exactly how to get started using GPU acceleration in your application in SuperVessel for the Developer Challenge. Then we'll take you through some additional learning and resources that you can reference later on, and we'll have time for Q&A, so you can ask a question through the Hangout anytime. On today's call, we have myself. If you've attended one of our Hangouts before, you've met me. I'm on the OpenPOWER marketing team, and I am driving the Developer Challenge. Mike Hollinger is usually with us. He may join us at some point. He's your go-to technical expert for anything related to the Developer Challenge. He's on Slack at MikeH-IBM. We also have IP from the IBM team. And today's call is all about NVIDIA GPUs, so we're happy to be joined by John Ashley, who's also, and our presenter today is Bob Cravella. He's a solution architect at NVIDIA. He's also in Slack, GPU channel, and you can chat with him one-on-one at Bob _ Cravella. So, you, Bob.
Okay, thanks, Beth. So what I'd like to do is I'm going to go ahead and share my screen, and what I'd like to do is do just some brief preparatory comments about what we're going to cover today, and then I'm going to spend probably the majority of the time here working directly in the SuperVessel instance and walking through some basic demos of how to use GPUs. But before we get to that, what I'd like to do is just sort of set the stage here. So what we'll be covering today is a very basic introduction to using an open road test machine instance that includes a GPU. So I'll show you how to set that up, how to launch an instance, a few of the basic setup steps that I would recommend after you launch the instance. Then we'll walk through hopefully a quick example of some very basic GPU programming using CUDA, a very basic example. And then we will, if time permits, I think it will, we will cover some more advanced topics that basically have to do with profiling. So we'll look at some very basic information about how to use the NVIDIA profiler that's included right on the machine instances with the CUDA software install. And we'll take a look at one or two slightly more advanced concepts with profiling. And we'll use a couple different codes to explore that. So there's some information that I'm not going to cover. If you're brand new to this, to the Developer Challenge, you will need an ID on SuperVessel. SuperVessel is the method by which IBM has made available machine instances in the cloud for all of us to use, not only for this Google Hangout, but for the entire Developer Challenge. And you will need to access SuperVessel in order to be able to launch the instances like I'm about to do. So there's a little bit of work you have to do that. IBM has made available some resources in a Getting Started guide, which I have listed here. And there is also a specific guide that's focused on the SuperVessel starting, quick start. So the resources covers a variety of information that you'll want to know regarding the Developer Challenge. The SuperVessel quick start guide really just focuses on how to get set up with your ID on SuperVessel. So I'm not going to cover it very well in that document. It's necessary for you all to do if you're going to use a SuperVessel machine instance. Also, I'm going to be using VPN. So as we'll see in a moment, it's possible to connect to your machine instance using the web. And so we'll start that way. But I will switch to using VPN. So it's a machine instance in the cloud. It has a method by which we can do it. It has an IP address that's available through VPN. I have set up the VPN on my machine. It's not terribly difficult. There is a guide that IBM has made available for setting up VPN. And you'll need to do that to get your VPN credentials. It's not difficult. but I have done that already. I'm not going to be walking through those steps. What we are specifically going to cover is going to our dashboard, logging into the dashboard, grabbing a machine instance, and starting up that machine instance. And as we'll see in a moment, there's the instance that we'll use is available in something called the instance market. I will connect to the instance over VPN. I've actually already done that in order to make this presentation flow more smoothly. So I'm not going to show you that, but that's a very simple process of firing up the Cisco AnyConnect client and just entering your VPN credentials in there. Once you've done that, then your machine can connect to your machine instance. Your laptop, let's say, can connect to your machine instance over VPN. I'll show briefly how to set up some CUDA environment variables, which are useful if you're going to be doing CUDA development work. I will show you how to build the CUDA sample codes, which are very useful for a variety of purposes. We'll look at some uses of those. And then lastly, we'll walk through, as I said, building a fairly simple CUDA sample code and then doing a couple experiments with profiling. And that'll give you kind of a rounded introduction to how to get started with CUDA on the machine instances and how to access some of the tools that are available. So I'd like to switch now to the demo session, and the majority of the remainder of our hour is going to be spent in this demo session. Towards the end of the hour, I think we'll have time for questions if there are any, and I will also cover some additional resources that I think will be useful if you have questions related to documentation or how to get help on the web, other online resources that can help you with CUDA programming, for example, as well as places where you can go to ask specific questions about difficulties that you may be having. So I'm going to go ahead and switch now to my instance, which I have pulled up already. So this is now in my web browser. I am looking at the dashboard. The dashboard is where you go to manage your instances. So this URL right here is the dashboard URL for anyone, and you can log in. So when you have a SuperVessel ID, you can log into your dashboard here, and you can see whatever instance you may have. Now, initially, you'll be presented with the Overview tab, and you probably, if you're just starting out like I was a while ago, you won't have any instances displayed here. I have an instance displayed here. That's what I'm displaying right here. This is an instance that I have already running, but I'll show you how to set that up. So typically, you wouldn't have any instances running, and you want to get started by launching an instance. So the easiest way to do that, and the only way that I'm going to show, is to go to the image market down here, which is actually a collection of different instance types, machine instance types, that IBM has set up already for this challenge. And depending on which track that you're going to follow in this challenge, you might want to choose some of these different instance types. You can see there are 5 different instance types that are available in this, for this developer challenge. However, the simplest track that we can start with, and really the only one I'm going to talk about today, is the Open Road track. And so the Open Road track is really where you can go and explore in kind of a blank slate format pretty much anything you want to do with Power or Power plus GPUs. So we'll take a look at this instance type here called Open Road, and I can get the details of it, but you'll notice that it has CUDA software installed on it already, so that's a good thing, and it has a GPU built into the instance. So when I pull up the details for this instance, it has CUDA integrated, it has a GPU built into the instance. So this is really what we need. It's got the IBM Power tools for building code. So this really has all of the basics that we need to get started. So I'm going to go ahead and launch one of those instances, and so we'll see what the process is like. It's actually pretty quick, much about the instance name, but you'll see that there are 2 choices here for the flavor, and the flavor really refers to how many compute resources you're going to have. So the smaller flavor has just a 2-thread system with, I believe, 2 gigabytes of storage, and the larger model has or the larger flavor, I guess I should say, has a 32-thread machine instance with a lot more memory associated with it. Probably if you're doing serious challenge work, most likely you're going to want to choose this instance here that starts, if you were using this open road image, you would probably want to use this 32-thread instance. It's going to have a lot more horsepower and it's going to have more memory, so it's probably the one that you want to use. But in my case, I don't need to do that. We're doing some very simple stuff today, and so I'm going to go ahead and leave it at the small instance. And I do want a GPU included this instance, so I'm going to leave that the way it is. And I'm going to go ahead and launch this market instance. And this actually launches pretty quick. I'm impressed. This will take just a few seconds, and it's going to spin up a machine in the cloud that IBM has provided. And this machine will be made available to us either through the browser or through basically an external IP connection. So that would be done over VPN, and I'll be talking about that shortly. But let's start with the browser. So right now we can see now that I've got two machine instances, and this first one is one that I've just spun up here, this one at the top. And so I can select this machine instance and choose to open a console onto this machine instance, which is great. So I want to do that. And in just a moment here, we're going to get a new console down here where it says Instance Console, and it's going to ask me for my login. Now you'll note that right off the bat, the information that you need to log in is right here in the browser header or in the console header. I'm going to log in as OP. I'm going to log in as OP user, just like it said, and then I'm going to enter that particular password. And right off the bat it says, since this is a new instance, this instance has never been booted before, it's brand new, right off the bat it says you're required to change your password immediately. So I have to change my password, but before I can do that, I have to re-enter the password I just entered. So I'm going to enter that same password again. Now it's going to ask me for a new password. So I'm going to enter a new password for this instance that's associated with the OP username. And there's some requirements for this password, capitals and smalls and whatnot. I'm going to let you read those. I'm not going to try and go through all that. But I'm going to choose a password that I think will work. Oh, sorry. Once again. That time it worked. So now I'm logged into my instance as OP user. And there's nothing in my directory right now. But one of the things I can point out is that if I look at this particular location, I see that there's stuff is there. This is a good sign. This means that CUDA is installed on this machine because the default location for installation of CUDA, if you don't choose a different installation, is right where it says user local CUDA. And I see that everything is there. All the stuff is there that I would expect to be there. Now, in order to start using the CUDA tools, I'm going to need some environment variables set up. So the way that I'm going to choose to do this, if I take a look around at what's actually in this instance, I can see that there's a .bashrc file. And I'm not going to go through the details, but this .bashrc file is set up to automatically source from a bash aliases file. So I'm going to go ahead and create that file. Bash aliases like that. And I'm going to put my environment variables in here, the ones that I need. So this is just a VI session that I opened in the browser. And I'm going to get my environment variables using bash just the way I need them. So that would be export, export This is defining the path to include the path to the bin directory for the CUDA tool. So that's really important because that will allow us to access the tools without having to type in the path name. And the other export that I'll want in here is for the runtime linker. And what I want to do there is just append the path to the CUDA libraries. I'm not really expecting you to remember this, but I'm going to show you where the CUDA documentation is later. And the Linux install guide basically has these instructions. So if you forget how to do this, you can just look at the Linux install guide, and it will tell you what are the typical path and load library path variables that you would want to set. So with that, I'm going to go ahead and save this file. And logging in to make this effective, I'm just going to go ahead and source this file. So right now, if I didn't do that and I typed nvcc-version, for example, Bash is going to tell me that it can't find it. But if I source my new aliases file, and now I repeat that command, then it can locate the NVCC, which is the compiler driver that we're going to use to build our CUDA codes. So there's just one more thing I really want to show you here on this instance that we just spin up, and that is that in the CUDA directory that I pointed out earlier, there's something called the samples directory. And the samples directory is a very useful directory that contains lots and lots of CUDA code samples that are complete applications that you can build and demonstrate all sorts of useful concepts for CUDA programming. I'm not going to try and go through all those right now, but what I'd like to do just to for instructional purposes is show you how to build those. So in order to build those, the most convenient way I know of to do it is to be a root user. And what we'll do is we'll go into that samples directory and just run a make file and let that run. So that means I'm going to need to change to be a root user, and I need to enter the password, and the password for root is also given, or let's say the initial password for root is also given here up in the console header. So that's just a slightly password than the one that I typed before. But unfortunately, it's going to ask me to change this password as well. So those are some of the security enforcements that they've made. So I have to re-enter this password that I just typed. And now it will let me enter a new password. So now that I'm the root user, I can actually go to this samples directory, and I can build this. It's conveniently set up with a make file, so the only thing I have to do is issue the make command, and that will then kick off the process of building a whole bunch of sample codes. So this make command actually takes a while. I'm not going to try and wait for this to be finished. At this point, what I'm going to do is switch to my other machine instance. So if you recall, if I go back to my instances page, I have two machine instances. One is the one that we've just been working on using the browser console, and the other one is this one right here. And you'll notice that when SuperVessel gives you a machine instance, it gives you an IP address. So we can use that IP address to connect to this machine instance. And you can use tools that hopefully you're probably familiar with, whatever your favorite SSH client is, and whatever your favorite file transfer utility is. You can use those directly with this IP address, just like you would with any kind of cloud-managed instance. The only wrinkle here, as I mentioned already, is that you have to first set up VPN in order to make this work. So I've already set up the VPN, and I've already actually spun up a PuTTY session connected to that IP address. So I now have this other session that I'm working in, and I've got a PuTTY client open and connected to this machine that I'm logged in via as the username OPUser. And I've been doing a little bit of work in this instance, so I've got a few files here, but not much. But this instance already has the samples built. So if I look at, I will see a new directory in here called bin. That's where the binaries are that were built, and the actual path that I need to negotiate is this. If I take a look in here, I'll see now a whole bunch of actual built applications that demonstrate all sorts of concepts. And we'll be using probably one or two of these. So just to show you as an example, I could run one of these directly. Let me just pick one called bandwidth test. And bandwidth test is a very simple utility that just measures various data transfer bandwidths, specifically between the CPU and the GPU, and also the bandwidth from GPU memory to GPU memory. So I can run that test very easily just by typing the full path to it. Like so, and this will now run the bandwidth test utility. And it's telling us that we've got a Tesla K80 device, which is no surprise. That's the GPU that's provided in this instance. We're getting about 7 gigabytes in both directions across the PCI Express bus, which is about right. And we're getting about 140 gigabytes per second of device memory bandwidth. So that all looks good. And I could run any of these other sample codes that if I wanted to. What I'd like to do now is really work with two codes. I'd like to spend a little bit of time actually just typing in a very simple vector add sample code so that if you're watching this Hangout session, you have a basic idea of how to program using CUDA. Now, this is not going to be a complete tutorial. There's not time for that. And when I get to the end of this session, I will point. You can go and spend an hour or two, and after that hour or two, you'll be a fairly proficient CUDA programmer. You'll have all the basics under your belt. This next 5 or 10 minutes is not intended to duplicate that. But if you have familiarity with CUDA programming, this is going to be very familiar to you. If you don't, this will outline some of the basic concepts that are needed for CUDA programming. But I'm not expecting that you'll get a complete brain dump of everything that's needed here. So we've already pointed out that NVICC is the compiler that we're going to use in order to compile CUDA codes. And typically when we create a CUDA code or a code that has something that's going to be running on the GPU in it, instead of giving it a .c or .cpp file extension, we'll typically give it a .cu file extension. And the NVICC tool actually uses that to make some decisions about what it's going to do. So we're going to create, using our VI editor, a new source code file called vadd, for vectoradd.cu, and this is obviously a CUDA source code file. So writing a simple CUDA program is really not that much different than writing an ordinary C or C++ program. So one of the things that I'm going to need is to include a basic header so I can have basic input-output. So I'm going to include IOStream, which is a good header for that. In CUDA, when I want to write a function that runs on the GPU, I usually annotate that with a specific keyword, which is _global. But the rest of the function very much follows ordinary C or C++ syntax for writing a function. So I'm going to write a vector add function. We'll just call this kernel add. All kernels in CUDA return a void type. We need to give it a name. I'll just call this add. And then we need to give it a parameter list, just like we would with any other C or C++ function. Let me go ahead and make this. I hope this isn't too complicated, but let me, well, we'll just make this work on floats. So we're going to add two vectors, which are given to us via float pointers, and we're going to store the result in a third vector, which is accessed via a float pointer. So we'll call them A and B are our inputs, and C is going to be our output. And we need to know the length of the vector as well for the addition. So we're going to call that size T B size. And that's pretty much all we need. Hopefully most of that looks like an ordinary function prototype if you're used to programming in C or C++. So we'll actually write the function code right now. Here's a new thing that's unique to CUDA programming. We have some built-in variables that we can use to differentiate thread behavior. So the code that I'm about to write is the code that would be running in a single thread, and then CUDA is going to auto-parallelize that to run across multiple threads. So I'm writing now the code that I would use to cause a single thread to add a single element of A to a single element of B and store that in its correct location in C. And I'm going to create an index variable that I can use for that using some built-in variables. I'm not going to try and explain these. That can come when you study CUDA programming if you're not familiar with it. But these built-in variables will basically create a globally unique thread index for me. With this globally unique thread index, I can now add an element from A using the index to an element of B and store it in C. So I'm going to say if my computed index is less than the vector size, then I want to say C of IDX equals A of IDX plus B of IDX. That is our complete kernel code right there. That is enough to do a vector addition on the GPU. The rest of it is just an ordinary main program, very similar to the type of main program that you probably know how to write. So we're going to need some variables. We'll need some host variables and device variables. On the host side, we'll have some variables called int HA, HB, and HC. On the device side, we will have some pointer variables called DA, DB, and DC. On the host side, we allocate for this using an ordinary host allocator function. I'll use new for that. So we're going to say HA equals new float. Oh, I called that int. I meant to call this float. We're adding floats here, not ints. New float of D size. I need a data size, so we'll say const int D size equals 10, and I'll need another variable here shortly, so I'm going to go ahead and put that in here. Number of threads per block, and we'll put that at 256. Those are pretty arbitrary for now. I'm not going to try and explain those, but once you dig into CUDA programming, you'll have a better idea of what those are for. But I need to allocate for A, so I'm going to allocate A of D size, and then I need to do the same thing for B and C. I now need to create similar variables on the device, and we use CUDA malloc for that. That looks like this. We pass the address of the pointer that we want to modify, and then we give it a size parameter. And that allocates on the device using that pointer for that size. We likewise need to do the same thing for DB and DC. We need to initialize our variables on the host. Okay, so now we've got some values plugged in for HA and HB. That's really all we need to worry about right now. At this point, we're ready for our basic three-step CUDA processing sequence. So every CUDA program, every program that runs on the GPU goes through exactly the same three steps. First of all, we have to copy data from the host to the device. We're going to use a function called CUDA memcopy to do that. It's very much like memcopy. So it takes a destination pointer, source pointer, size of transfer, and another enum type, which is the direction of transfer. And so that will copy our A vector from the host to the device. We can do the same thing with our B vector. And that completes step one of our CUDA processing sequence. Step two of our processing sequence is to actually launch the kernel. So this is what kernel launch syntax looks like. It looks a lot like calling a function. So we use the name of the function when we call it. So we're going to say add. And the thing that is different about CUDA is we've got this triple chevron syntax, which defines the auto-parallelization that happens on the GPU. So I'm not going to go through this in detail, but ultimately, this is going to spin up enough threads on the GPU to cover the problem space. So just bear with me as I type some of this arithmetic. It's not too complicated. There's basically just two parameters that I'm entering here. So I'm going to take the data size. I'm going to increase it or round it up to the next even block size. And I'm going to divide that by the block size. That will be the number of blocks that I launch. And this is the number of threads per block. That's just the two parameters we need there. And the rest is just passing the necessary parameters. So we pass DA, DB, DC, and DSize. And that is a kernel call in CUDA. The third step of our processing sequence is to copy the results back. We're going to use another CUDA memcopy operation for that. And in this case, what we want to do is copy the results into the C variable, or the C vector. And this direction of transfer now is from device to host. You'll notice that as I've been doing this, that nowadays VI actually has syntax highlighting for CUDA, which is kind of nice. Okay, so we have now completed the third step of our CUDA processing sequence, which is to copy the results back. The only thing left is for us to inspect the results. So we'll do that with just a simple loop. And that is the end of our program. That's a complete CUDA vector add program. Okay, so now that I've typed it in, we can save it, and I can compile it. Compiling is pretty simple. If you're familiar with like GCC syntax, you'll find the NVCC syntax very familiar. We just give it the name of the file to compile, which is vadd.q, and we specify an output file name, which we will just call vadd. And if I haven't made any syntax errors, then this will just compile. Now that we're ready to run it, a convenient thing to do, especially I would recommend if you're starting out with GPU programming, the first time you run a program is always run your programs with CUDA memcheck. I don't have to do that. Just like I would with an ordinary Linux executable, I can just launch it this way, and we see that we get the correct results. But CUDA memcheck is a utility that's sort of something like Valgrind, and it will find a lot of errors that may not be obvious if you just run the program without it. So I always recommend for people who are beginners to run their programs with CUDA memcheck, just like I have done there. But nevertheless, we see the results that we're expecting, right? Our vector length is 10, and we're adding I and I plus A and B, and we're putting out the results in C. So this all looks good. Fortunately, I didn't make any mistakes. So what I'd like to do now is show you how to use the profiler. The profiler is available from the command line using the command line tool called nvprof. And the most basic, I would say the most basic thing that we can ask the profiler to do is to print a GPU trace, just like that. And this says to the profiler, basically just give me an annotated timeline of activity on the GPU. And so then we just tell it which code do we want to run. And this will run the code, and then it will give us some output. And we see in the output here that we did, sure enough, we did 2 CUDA memcopy host-to-device operations. Then we launched our add kernel, and then we did a CUDA memcopy device-to-host. So the GPU trace appears to be correct. It appears to be what we would expect. There's some other information here, quite a bit of other information, actually. We can find out how long things took to execute. So this add kernel took only about 4 microseconds to run. We can find out how much data was transferred. So over here we see that 40 bytes of data was transferred in each of these operations. We see throughput numbers, what device did it run on, and lots of other information as well. I'm not going to try and go through all that, but this is a very basic way to use the profiler. And if your application is relatively simple, like this one is, then this is probably sufficient. We can get most of the information that we would want just looking at this kind of output. But suppose we have a more complicated application, and so for that, I'm going to switch gears, and we're going to take a look at one of the applications that we built when we built the CUDA samples. This is actually the directory where we built all the samples. I can see all of them there. And the one that I'm going to focus on is the CUDA reduction sample. So that is this one. And we could take a look at the source code, but we don't really have time for that. So what I'm going to simply describe is that this is an application that demonstrates how to do what I would call a classical parallel sort of algorithm that takes a large data set as input and produces one or a small number of numbers as output. For example, if I wanted to sum all the elements of an array and produce one number, the sum, that would be a classic example of a reduction operation. And a reduction operation, if you think about it, is a very straightforward thing to write in serial code. I can do it with a very trivial loop. But to do it in parallel requires a little bit of thought and a little bit of additional effort. And so writing a proper parallel reduction is something that CUDA programmers may run into at some point, learning how to do that. It's sort of a basic principle when it comes to CUDA programming, or a basic concept that you can have under your belt. Anyway, that's what this sample code does, is it demonstrates in a very straightforward fashion how to write a reduction. And it's written to be something like a benchmark, so it's actually doing a number of things under the hood. So rather than getting too much farther into the description, what I'd like to do is just run it with the profiler, just like we did with our very simple vector add code. And so we can run the profiler from the command line saying nvprof print GPU trace is a very basic trace-like output. If I could type. And we can run our application that way. And so this is going to run the application, and then we see a lot of output. And so if I wanted to, it's not terribly difficult. I can use the command line profiler output and wade through this, and I see basically that a reduced 6 kernel is being called over and over again. But there's a little bit more detail to this, what's going on here. And it's not that easy to pick out from this, although if I spend some time decoding this, I could. What I'd rather do now is demonstrate how to generate profiler output that will be something that I put into a graphical tool, and I'll demonstrate that in just a moment. This is a good time for me to show you the CUDA documentation. So the documentation for CUDA, the most convenient place is at docs.nvidia.com. If you go to docs.nvidia.com, to this page, which has all of our CUDA published documentation. And what we see on the left-hand side here is basically a set of books or manuals in our library. So if I'm interested in a particular topic, like how does the NVCC compiler driver work, I could get the manual for that. What I'm interested in now is the profiler. So there's a manual for the profiler. And I'm interested actually in the visual profiler, because I'm going to ultimately be getting to the visual profiler. But before I do that, you can see that we're using the NVProf profiler that's described here. And in order to use the visual profiler with NVProf, I'm going to need to choose a particular output format. And the output format I want is for an import session. So I'm going to import a single process NVProf session. And the typical parameters that I would pass to NVProf are described here in the documentation, so that I can import a single process NVProf session into the visual profiler, which is the graphical tool that I'm about to demonstrate. So I'm just going to modify my profiling now to use this export profile option. So I'm going to rerun the NVProf thing that I just did, and I'm going to say -- export profile, and I'm going to give it a file name, prof1.out. And the rest of the command is just the same. And this will run the application just like it did before, but it's not giving us all the output. Instead, it's creating this file called prof1.out. And that file presumably encapsulates the information that we just looked at in command line form. So here's the cool part. I can now pull this file off of this machine instance. So just like I'm connected to this machine instance using SSH with my SSH client, PuTTY, I can also connect to the machine with a file transfer utility. So I'm going to use WinSCP to do that. Again, you'll need VPN for this to work. But I've already set up this machine as a session in WinSCP, so I can just go ahead and log in right now. And it's going to ask me for my password, so I'll enter that. And I am now logged in, and I can see I've got I'm taken to my home directory, and right there is my prof1.out. So I can just pull this off the machine instance and pull it over to my laptop just by dragging and dropping like that. And I can now see in my laptop documents directory I've got prof1.out. Now on my laptop, so I'm not on the machine instance anymore. On my laptop, I can open up a command prompt and type NVVP, which is how I launch the visual profiler. This will take just a minute to start, but this is a graphical tool which can use the output effectively from NVProf to show you a lot of interesting things about GPU programs in a graphical way. And so what I'm going to do once this application starts is I am going to import that file that I just moved over from the cloud to my laptop, and we're going to see if we can discover any other interesting things besides just seeing a list of kernel executions. So I'm going to import a session, so I'm going to open an existing session. There's my prof1.out that I just grabbed, that I pulled off of the cloud machine and brought over to my laptop. I'm now opening the file, and what we're going to see is the first thing that the profiler does, and really the main thing I'm going to talk about, is it gives us a timeline. Instead of having to look things in text format, it's going to show us a nice colored timeline with multiple categories of activities that are going on and when they're happening in the overall execution timeline. So let me zoom in a bit here, and what we see is there's actually kind of a repeated sequence of stuff that's going on. We'll take a much closer look, but right up front we see that there are these memcopy operations from host to device. That's no surprise. Like every CUDA processing sequence, the first step is to get data to the GPU. So the first thing that we're doing in this application is transferring the data to be reduced to a single value down to the device, and that's what's going on here. Okay, and we've actually got a separate bar for activity in the host to device direction, a separate bar in the device to host direction, for example, and then we've got other bars that show us compute activity that's going on in the device. And now what we see is a little bit more detail. Instead of just seeing a sequence of kernel calls, we see that there's an alternating pattern of long kernel calls and short kernel calls. Most of the time is being spent in this type of kernel call on this timeline, but interspersed we see very short kernel calls. And this is actually characteristic of a reduction, or this particular reduction, which is basically processing the data in two steps. It's doing a large-scale reduction first and then a final reduction to produce a single number second. And if we drilled into the source code, we would discover exactly that pattern is going on. We'd have kernel launches that are launching first a larger kernel, then a smaller kernel. The other thing we see is that there's a lot of these that appear to be going on repeatedly, and that's true because this application is actually launching a whole bunch of these basically for the purposes of benchmarking, to average out timing differences. It's just good benchmarking practice to do that, to repeat the process multiple times to average out small differences. Finally, at the very end of our application, we see that there is this very tiny little CUDA memcopy operation in the device to host direction. And that makes sense because in the beginning we transferred a lot of data, all of this data, so that took a while. But the reduction operation reduced that to a single number. And a single number here takes almost no time at all. And as we see when I click on this, I can get additional specific statistical information about this data transfer. It was only 4 bytes long because it's just a single number that's being transferred from device to host. So that's a quick walkthrough of how to program the GPU, how to use the tools that are available on the OpenRoad instance, how to set those up and use those using the compiler, using the profiler, how to edit code, and how to compile code. And we also saw at the end how to actually take advantage of CUDA tools that you may have installed somewhere else. So I have the CUDA tools like the Visual Profiler installed on my laptop, and that's a convenient way to work when you're working with any machine in the cloud instance where you probably don't have or don't conveniently have the ability to run graphical tools in the cloud. It's easier to run those tools locally, so that's what I've demonstrated here. So with that, I'm getting close to the end. I've completed most of what I wanted to do for the demo portion of this. And so the last thing that I want to do is talk about some additional resources that are available. So I'm going to go ahead and switch back to my PowerPoint now. And I just want to walk through some of the additional resources. The first one that I've listed right there is just where the docs are located. The NVIDIA published documentation. That's at docs.nvidia.com. And as we saw, that basically looks like a library, if you will. A library that has a bunch of books in it. And the books are all listed on the left-hand side. And when I drill into one of the books or one of the manuals, I'll see the chapters that are in the manual. If I want to get back to the overall library, I just click at the top here, and I can switch to another book in the library. If I want to learn about programming, you could actually read this programming guide and become a pretty good CUDA C programmer. That's another way to do it. But this is kind of the canonical repository for all of the documentations, and there's a good chance that most of your questions are answered here somewhere. So that's a good resource for you to have. Another resource that I want to point out is that NVIDIA archives a lot of information with the GTC tag. The GTC tag is actually referring to GPU Technology Conference, which is annual or multiple times per year that NVIDIA runs large-scale conferences where we disseminate a lot of information, and a lot of our users disseminate information. So we present technical papers, and there's workshops and all sorts of sessions that happen at a GPU Technology Conference. So we try and archive most of that, the papers, the presentations, and even video recordings of the presentations. And so when you Google search for something with GTC and let's say CUDA, GTC CUDA Intro, or GTC CUDA Optimization, let me just quickly show you how easy that is to quickly find very useful information. So if I pull up my browser and open up a new tab and search for GTC CUDA Optimization, within the first few hits, I'm going to find this is GPU Performance Analysis and Optimization, is a presentation that was presented by one of our ninjas at NVIDIA, Paulius. I'm not even going to try and say his last name, but Paulius is a coding ninja. He's an optimization expert, and if you pull down this PDF file, you'll be able to have a very good walkthrough of first-level optimization and analysis that you would want to do on a CUDA code. Okay? This is not for beginners. There's other presentations that you would use for beginners. So I would say something like GTC CUDA Intro would be a good starting point for beginners. But once you've had an opportunity to look at some of the GTC sessions that introduce CUDA, then you could go ahead and look at that optimization. And between those roughly 2 hours of material, that's a very good introduction to programming GPUs. So GTC CUDA with your keyword of interest is a very good way to find resources that are going to be curated and high quality. We also have some guided resources online, and these take the form of an actual lab that you would run. And so I'm not actually going to try and run one of these labs, but I'll just pull up the entry portal to it. It's at nvidia.quicklab.com, just like I've shown here, and the link is in the slides as well. And when you go to this portal, you'll be presented this is an online portal that allows you to access training content that's grouped into classes. And each class that you take can increase your knowledge about GPU programming. And you'll see right off the bat, we've got a track of classes identified here called C, C++. So I can look at all the labs in this quest if I wanted to, and I would see that there are something like 4 or 5 classes, each of which is about an hour long, that I could take, and I would learn basic introduction to GPU programming. If you take one of these classes, what you'll be presented with is organized material basically in an IPython notebook. So it's a mixture of text and pictures, basically training material, along with actual coding exercises that you can run right in the IPython notebook. And those exercises will actually run on a cloud. So even if you don't have a GPU, you can take this and you can write CUDA code or GPU code and run it in the cloud. So this is a very convenient, a very organized way to teach yourself, if you will, self-guided approach to learning how to use GPUs. A number of the courses are free. Some do require credits. Credits is our way of preventing misuse. We're not really trying to prevent people from taking the classes. You can certainly buy credits if you want to, but if you contact me, let's say in the Slack channel, and explain to me what you're doing or who you are, I'll be happy to arrange for you to get credits so you can take some of these more advanced classes if that's what you'd like to do. So that's another very good resource basically for just learning CUDA or learning GPU programming. When you have questions, you may want to use some of the available forums. One of the available forums is right here at NVIDIA, or sorry, at devtalk.nvidia.com. Another forum is on Stack Overflow. I'm actually one of the contributors, or let's say one of the people that tends to curate the CUDA tag on Stack Overflow. So if you have CUDA questions and you post them in the CUDA tag, I'll almost certainly look at the question, and there's some percentage chance that I will try and answer the question for you there on Stack Overflow. devtalk.nvidia.com is basically the same idea. It's forums, and there are some that are specific to CUDA programming. In order to use that, you need to become a registered developer, which is another concept that I've depicted on this slide. You can do that by going to developer.nvidia.com. If you are not on Slack or you need help with learning how to use Slack, you can get information about how to use Slack here. I'm now on Slack. It's Bob_Cravella, which Beth already mentioned. And there is actually a Slack channel where you can post questions about GPU programming. It's called NVIDIA GPU, which I will try and pay attention to that Slack channel. I'll do my best. I'm still a little bit new on Slack, so you're going to have to cut me some slack. But if you ask a well-formatted question, let's say on Stack Overflow or devtalk.nvidia.com, I'm sure you're going to get a very productive answer for you. Last, there's lots of resources that are just available for general OpenPOWER or the Developer Challenge questions that you may have about that, and I've included the link there to help you get started there. So with that, it looks like I have maybe 5 or so minutes left. I don't know who may be listening, but I'm going to try and stop talking, maybe turn it back over to Beth, but I will try and answer any questions if there are any at this time.
Thanks, Bob. Yes, we do have a question. You might want to get in a position to pull up your program,
okay.
Your vector add program.
Okay. I think I pulled it up.
Great, thanks. So the question came from Kieran, and he was asking, so does the call to the function add have 2 extra arguments than its prototype parameter list?
So the prototype parameter list is here, okay, and the argument list is here. So we see those matching 1 for 1, right? We've got float A and we're passing dA, float B, dB, float C, dC, dsize, and dsize. I believe what's being asked is here. It looks like there are 2 additional parameters here, and that is correct. Those 2 parameters are specified by this comma. And this is really what makes ordinary function call syntax different than this, which is what we would call kernel launch syntax. So these are the kernel launch parameters. They're not part of the ordinary function parameter list, which we see up here. Okay? The kernel launch parameters are effectively the same for every kernel. Any function that you want to run on a GPU is going to have the same parameters in the same order. The first parameter, which is a mandatory parameter, is the number of blocks that you're going to launch. This, as I mentioned, is the first 2 parameters are related to the auto-parallelization process that is inherent in the CUDA program. So in the CUDA programming model, as I mentioned, when we're writing the kernel program, we're writing it from the standpoint or in the context of an individual thread. Fundamentally, the thread code up here is asking or answering the question, what will a single thread do? Okay? Then what we're going to do is differentiate that behavior from thread to thread using things like indices, which vary by thread, and then we're going to launch multiple threads. And the way that we launch multiple threads is a hierarchical way that starts out by specifying a number of blocks, which I have specified here, and a number of threads per block, which I have specified here. When I multiply these 2 together, I can determine the total number of threads that CUDA will spin up as part of the auto-parallelization process when it launches this kernel. And it means that this code will run, this code up here, will run across this many threads, the product of these 2 numbers. So we don't see these two numbers in the ordinary function parameter list because they're not part of the ordinary function parameters. They're unique and specific to CUDA. They're the kernel launch parameters or the kernel launch syntax, and they are parameter-wise, they're the same for every kernel launch. It doesn't matter what your kernel's doing.
Okay, thanks, Bob. And that was the only question we had. There was one question about the screen sharing being a little blurry, but I apologize to the viewers if that was happening on your end. So I think that is about a wrap. I would like to thank you so much, Bob, for taking us through this demo, and I've shared all the links for viewers. A great way to get in touch with us would be in the forum of the DevPost site, and preferably the Slack channel. It's a little bit more dynamic. And we are planning some more educational opportunities, so we'll have some stuff that we're planning and we'll be broadcasting out to you. But what would be even better is if you could get in touch and tell us what you'd like to hear, because we've gone through the basics today of GPU programming, but we're asking you in the developer challenge to do giving you some more sophisticated opportunities involving deep learning and Spark. So let us know what more you'd like to hear about in more depth, and we'll be happy to get in touch with you. So thanks to everyone who joined us, and thanks again to you, Bob.
Thanks, Beth.
All right. See you guys next time. Bye-bye.